Okay, and the next speaker is Professor Ismo Koponen from the Department of Physics at the University of Helsinki. And he has worked also with physics education. And I think he's one of the few people in Helsinki and Finland who work on quantum foundations. And of course, we're extremely happy that he's with us today. I think afterwards he's going to heading to Karonka. There's lots of PhDs happening in Finland this week. Yeah. And I think are you at the custos or the opponent?
No, I was the supervisor.
Supervisor, okay.
So my apologies, this is not my usual attire to give a presentation in a symposium, but I'm attending a formal party afterwards.
Dress for the occasion, there we go, please.
Okay, thank you. My topic is much more mundane in comparison to Avril's, and it's very focused on the wave-particle duality. You know that wave-particle duality is a topic where a lot of ink has been spilled on writing about wave-particle duality, and it has been declared dead at least 3 times. Willis Lamb declared it to be dead. Philosopher Mario Bunge declared it to be dead. And probably you don't have any problems to find philosophers, physicists who say that wave-particle duality is dead. So it may appear that there is not a lot to say about the wave-particle duality. But if you take a look on the recent 15 years on quantum optics research, you see a plethora of papers written about wave-particle duality or wave-particle complementarity in modern quantum optics in interferometric experiments. Usually the topic of these papers, which are probably a couple of hundreds, is the quantification of the wave-particle duality. Or sometimes it's discussed whether these modern experiments, whether they refute or support Bohr's ideas about the wave-particle duality. So it seems that in case that wave-particle duality has been dead at least 3 times, it's doing well again. Why? And what has happened? And my point is that perhaps wave-particle duality, after all, is not so much about ontology, not about the properties of the particle or wave properties of the quantum phenomena, quantum systems. It's more pragmatic. It has a pragmatic value about speaking of the experiments. Well, I try to motivate this kind of understanding to pay attention on certain aspects on this question of wave-particle duality. The wave-particle duality actually has very different meanings. It's not obvious what we are talking about when we are talking about wave-particle duality. Very often people are referring to old problems of radiation, speaking about Einstein's understanding versus Bohr's understanding. And of course, it's historically correct. This discussion went on. But eventually, in 1927, these questions came to be asked about quantum particles like electrons and especially also photons, whether these single entities somehow exhibit wave-particle duality, either in their behavior in the experiments or whether it's a kind of intrinsic property all these quantum entities have. And Bohr, in his Como lecture, framed some ideas related to wave-particle duality. And then he attached these views on the idea of complementarity. Bohr thought that wave-particle duality is an example of complementarity, but he changed mind. In later writings of Bohr, 1935, he doesn't anymore think that wave-particle duality is kind of example of complementarity. And then wave-particle duality begins to disappear as a topic related to ontological questions in quantum phenomena. But then what Bohr begins to speak about is the appearances in experiments, how experiments need to be communicated in terms of the classical concepts. And in this situation, how we speak about the outcome of experiments, wave-particle duality, is now a common language expression, what we experience in the experiment. And it's no more related to ontological questions, it's related to pragmatic questions to communicate experimental results. Very much of the older literature failed to pay attention on this kind of aspect on Bohr's writing. But during the last 30 years, several philosophers and historians of science have noted that actually there is this kind of change in Bohr's thinking in 1935. So wave-particle duality becomes a kind of pragmatic semantics to speak about things, to communicate things. Bohr says that how other way we could speak about experimental results we find out in different kind of doable, realizable experiments. And then we have many views by philosophers, what Bohr actually meant about this wave-particle duality. There is a diversity of views. Everybody can probably pick out his or her own favorite of these views. And so I'm not saying that my understanding of Bohr's ideas or my understanding of philosophers' interpretations and historians' interpretations of Bohr's ideas are the correct one, but it's at least one possible one and one plausible one. And then, as Willis Lamb, also Lande and Beller, and later also Mario Bunge before them, they have had very negative ideas about the wave-particle duality and thought that it should be deleted from the physics vocabulary, and it's completely useless. But still, physicists are using this expression, wave-particle duality, in publishing research papers in physical journals. So it must have some advantages. Let's skip this one. So now, why wave-particle duality actually was reborn? We can locate one event or certain events going back to Wheeler's ideas and Wheeler's way to understand Bohr's complementarity in delayed choice experiments. Wheeler and Zurek in the end of the 70s suggested an interesting thought experiment, a delayed choice experiment where they claimed that actually Bohr's ideas about the exclusiveness of the wave and particle aspects in certain experiments, it's not valid. We can make a much smoother observations, observe in the same experiment both properties in these delayed choice and which way experiments. It was only a thought experiment, but it boosted a kind of renewed interest, the wave-particle duality. And reason was that Wheeler and Zurek, they connected these new ideas to quantum information-theoretic ideas, so that actually what they were talking about was a control of quantum coherence and quantum correlations in systems where we have entangled states. And in a way, it originated at the same time also the new research field of quantum information and how to understand quantum phenomena through quantum information. And that's why it took some interest by other physicists and researchers. And then the first experimental advancement with the single-photon sources made by Aspect, Rogier and Grangier, which developed in those experiments where they attempted to test the EPR paradox and Bell inequalities. They already had invented the way to create single photons in atomic sources, and that opened up a completely new possibilities for quantum optics to study this kind of phenomena which were originally related to wave-particle duality. And then we have also many theoretical advancement discussing the wave-particle duality, or sometimes called wave-particle complementarity. Physicists are unfortunately not very careful in their terminology. Obviously, when they speak often wave-particle complementary, but you look what they are doing, they are actually again doing something related to wave and particle nature of quantum states and how these aspects are related to quantum coherence and quantum correlations. So more or less it's exchangeable in the research literature. Also in philosophy of science, there is renewed interest towards wave-particle duality, and also how these contemporary ideas are now related to Bohr's original ideas. These are only some examples of these topics. You can easily find many more. So it appears from the dates of all these papers that the wave-particle duality is far from dead. It's doing well again, but now perhaps in a reborn way. So now what might be the connection of Bohr's ideas to contemporary ideas? It's a kind of possibility to locate the quantum state in a certain part of the quantum interferometric systems, typically a kind of interferometer, Mach-Zehnder interferometer, Sanyang interferometer, Michelson interferometer, which have distinct parts. And if it's possible to say that now we will have a quantized electromagnetic radiation, quantized light in this part of the interferometer, and it's a state or case where we have a weak enough light that it can be described by concept of single photon. Now, it's very important to think that single photon in this case is not to be taught as a kind of particle or some kind of entity. It's the quantized mode of freedom of the electromagnetic field described in terms of the Fock states in Hilbert space. Technically, it's the eigenvalue of the number operator in this case. But nevertheless, the state of the quantum light, it can be detected that we have large probability to detect a single photon in this part of the interferometer. And then we can speak about distinguishability, predictability of the photons' location on these devices we are doing the experiments. So now the whole picture is that actually our theories and understanding is not about some external photon coming from somewhere, coming through a measurement device, but instead we have a phenomena which is contextualized in an interferometer in a single device. And we are attempting to make accurate predictions what will happen in this kind of situation. And it gives the interesting possibility to control quantum phenomena. Actually, it's on the core of the ideas of quantum computation and quantum technology that we can control qubit states in different kind of systems by using the quantum optical theories. So now these quantities, distinguishability and predictability, can be related directly to quantum theoretical description of the quantum state of light in these kind of devices. And then it will take the role of particle. But as you can understand now, it's only some kind of subset all of these properties classical particles have. It's a kind of distinguishability, predictability, some kind of possibility to predict where our interesting state is. And then we have, in addition, the visibility, which is related to wave kind of properties through the interference effect, that when we see in these experiments accumulation of interference kind of number density of observed events. I said it in this complicated way because very often it's said that we observe in this kind of situation interference pattern, but it's not true. It's not classical interference pattern. It's an accumulation of single observation events which has a mathematical form of interference pattern, but it's different thing. So then we can speak about visibility, which we can attach to wave-like properties in the sense that now we are attaching it in the properties of the coherence of the quantum states. When we lose the coherence, we lose the interference, but when we don't have the coherence, the states are incoherent, then we have this particle kind of observations in experiments, and we can speak about predictability and distinguishability. So what has been done? The wave-particle duality is now related to theoretical quantities. It's not anymore external philosophical principle interpreting, but it's a quantity which is derived from theory and which can be operationalized in certain quantum optical experiments. But for researchers, it's convenient to speak about wave properties, particle properties as a kind of shorthand notation. And these ideas relate, they lead to different kind of inequalities where we have certain possibilities to observe either this distinguishability or visibility, and we have plenty of these kind of inequality relations derived in different ways, more complicated than these two ones, but very often we are speaking about these simplified versions. Now a short remark. I won't speak nothing about more modern experiments, weak measurements, and non-invasive measurements, because in this case there is still another interesting step of evolution where we have now quantum complete complementary relations which are entirely theory dependent and which are very valuable in controlling the quantum states. But to keep this short and comprehensible enough, I will focus on these more simple cases. So in what sense, if any, there are any connections to Bohr's views? Sorry. And some researchers think that no, they think that these are completely different things and there is no relation. Well, I think a little bit differently. This is true if we focus on physics only, but if we focus on more practical aspects, how researchers are doing experiments, what they are speaking about in doing the experiments, and how they are communicating the results, we find quite useful uses for wave-particle duality, but then we need to remember that it's only way of speaking. This is actually something a very well-known figure in quantum optics, Englert, has very many times reminded that wave-particle duality is something we physicists use in speaking in their doings, but it's not related to theory of physics, not very deeply. So it's a kind of way of speaking. And so my boring suggestion is that Bohr's wave-particle duality has nothing to do with ontological epistemical questions. This might be a kind of anticlimax. It's only a very pragmatic thing related to pragmatic semantics. There are some philosophers who very clearly bring this idea forward. For example, Osnagi, who is actually practicing physicist, but also has written about philosophy of science and makes this point. Also, Camilleri is well known of these kind of ideas. And this is very well aligned with Bohr's later ideas, where he relates wave-particle duality as a communication and way to communicate the experimental results. But unfortunately, this is not very often appreciated by people who write about these kind of things. Here are some other quotations from Bohr, where you can see a similar kind of attitude to wave-particle duality. So this is late Bohr's thinking, when Bohr already had changed his mind. And actually, from this perspective, Bohr's philosophy of quantum physics is not so much about philosophy of physics as a theory describing world or representing world. It's philosophy of knowledge, philosophy of how we acquire knowledge, how we speak about knowledge, and what kind of knowledge is accessible in experiments we can do. There is great temptation, I think, referring to Avreli's presentation, that this is instrumentalist position. But it's not. It's instrumentalist only if we forget the important role experiments have in this kind of situation. And experiments are the bridge to reality. And it's not just ordering experimental evidence. Of course not, because the point of doing these kind of things is to achieve a kind of control in very complicated physical systems, which of course tap the reality. But what we need to be aware and be very careful is that we don't make the reification of the mathematical concepts so that they describe directly reality. If we have in theory the idea of photon as an eigenvalue state of number operator, it doesn't mean that photon is an entity which have intrinsic properties which can be somehow revealed in experiments as particle or wave-like properties. So just a very short look on Grangier experiment. In Grangier experiment, it was a Mach-Zehnder interferometer with the single-photon source. This I can skip, but here you see the outcome of the experiment, where you see the accumulation of the single dots so that they form an interference-like pattern, but it's actually a number density distribution, not continuous, but discontinuous. And what is important that we have two detectors here, and both will observe this kind of interference-like accumulation probability density, but they are completely anticorrelated. And the anticorrelation is very importantly related to question that we can be sure that we have only single photon state in these kind of systems. And of course, we need this if we want to achieve a kind of understanding and control of qubits, for example, which are single photon states or two photon states. So this is the first experiment. So how Grangier et al. Themselves interpreted this thing. They made an interpretation where they noted that, well, this aligns well with Bohr's ideas, how these things are related to outcomes of the experiments, the appearances of the experiments. But, and this is very good, I find this very nice way to express what they found in their experiments. But then they say, here is the but. They say that from the point of quantum optics, we will rather emphasize we have demonstrated a situation with some properties of single photon state. And then they go on to discuss the density matrix, coherent states, mixed states, pure states, and such things. So now they are relating this question directly to quantum optical theory, no more the philosophical ideas of wave-particle duality. And in a sense, you can understand the relation between different concepts and terms like this, that we have here the terms of interpretation, single photons, Bohr's wave-particle duality, their properties, no split photons, and so on. But then we have here the classical experiment, the classical concepts which we use in speaking about these final outcomes of the experiments. But actually, we are using the quantum theory of light to make sense what happens in the interferometric experimental setting, and how actually we can explain and understand what happens in this special case. So everything is very strictly contextualized, and we use the quantum optical theory, quantum theory of light. And then we have a more complicated experiments with variable interferometric settings, which allow us to test these complementary inequalities, where we don't have pure interference and pure particle-like behavior, but instead we have something between to realize the Wheeler's and Turek's original idea. And one of the most convincing experiments are by Jacques, also involving Aspect and Aspect's group, which show here how this inequality, how this inequality becomes realized in these experiments, confirming the information-theoretic entropic inequalities derived from the theory. So now we have the complete picture. We started with the Bohr's philosophical ideas, everything was abandoned, and now everything is based on theoretical ideas, so that these quantities are derived from theory, and then they are operationalized in experiments as good physics need to be done in instrumentalistic way. Thank you.
Voinko mä laittaa, kun meillä on... Tai jos sä osaat laittaa sen Zoomin pyörimään paremmin. Otetaan, any questions? Peter?
So you were saying really that the duality is a choice we make, the experimentalist, or at different stages of your
yes,
experiment.
basically, yes, that we can use the expression of wave-particle duality in meaningful way to speak the appearances in experiments, but in the deeper level, we are actually speaking about quantum coherence and quantum correlations, which if we take a closer look, all the quantum states we are dealing with in these interferometric settings, they are actually, in a sense, wave-like. They are quantized states of electromagnetic field inside a certain device. And the description of the device in von Neumann's way is inherently connected to how the quantization of the electromagnetic radiation happens inside. It's very contextualized. But still, we can meaningfully use the expression if we understand what we are speaking about, and I would say that don't take it too serious.
So the duality is there more in our understanding.
In our understanding, the natural way we are accustomed to speak,
So
because
it's still an open question in a way.
in a way, yes, what it actually means.
Yeah.
Yeah.
Okay, maybe we move on as we are going to have to leave the building anyway. But thank you so much, Ismo Koponen.